And so we're going to get into this vector model. And so just to kind of remind you, we've already talked about the right-hand rule for angular momentum. But I also want to remind you, if let's suppose I have some vector, okay, so I'll draw like a XYZ coordinate system. Okay. Perhaps this is X, Y, and Z points up. All right. So if I draw some vector, so I'm going to draw some vector in the going into the ZY plane, right? So, and I don't know why I chose to draw this so small, but we're going to go with it. So that vector, I'll remind you, has components in the Z, X, and Y dimension, depending on how we've drawn it. Of course, this one I've only drawn in the Z, Y plane, which means now if I'm going to change my color here. So that means this vector would have projected magnitude on the z-axis, or really I should say projected length on the z-axis. It would have also projected length on the y-axis, right? And if I add those two projected lengths up, then I get the total magnitude of the vector, okay? So let's label those. Let's say total magnitude. And of course, that total magnitude is going to give me the length of that vector. And I'm going to call these, the blue areas, the projected lengths. Okay. And of course, with this vector, the way I've drawn it, we'd have projective lengths on the z and the y. But what if I gave my vector some pitch, right, out into that x dimension? So then, of course, we would have projected lengths on the x, y, and z. And we would have to use this full three-dimensional cross product to describe that vector. And more importantly, what we're really interested in, right, is describing this vector as angular momentum, right? So if you look at my picture here, and I just noticed I got this picture from Atkins, and it's drawn wrong. They violated the right-hand rule. So right, if that vector is pointing up this way, it should be rotating the opposite way. In any event, right, when we see pictures like this, we want to represent this angular momentum as this three-dimensional vector representation, okay? So here's how we do it. We use the determinant, okay, R cross P, and so you might have just talked about this very, very briefly in some of your math classes, but I'm going to go through this to remind you, okay? So L hat. So now when I go through this, okay, I'm going to start with vector I, right? So each of these vectors, I, J, K, give us the, the projected X, Y, and Z vectors, right? That's what the I, J, K stand for. And so the way that I do this, okay, so if I start with I, then I go down the diagonal, right? And that's going to be Y times PZ minus Z times PY. Okay, so I'm going to put that in red so that we can see what's going on. So I'll say dot, 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 dot. We start at I and we go to Y. Okay, and so then we say Y times PZ minus Z times PY. All right, so that's going to look like this. Let's see here. Y hat PZ hat minus Z hat, PY hat, parenthesis, and that's all times vector I, okay? And so now we've got to keep going with the other dimensions. And so I didn't leave myself enough room, so I'm gonna, on this next line down here, I'm gonna say minus. So right, we keep summing up all of these projected lengths. And so now when I go to J, all right, let's get a different color for J. So when I go to J here, I'm going to now go over, I'll draw a dot to the x, okay? And now I do this diagonal, okay? So where I'm going to go now x, pz, and z, px, okay? So that gives me like so and like so, okay? So let's see here. So now I've got that as x, yep, x pz minus z px, okay? For some reason, I just doubted myself for like half a second, so I'm just going to verify that I did that correctly. Yes, xpz minus zpx. Okay, beautiful. So there's the z, and then now that's times vector component j. And then now finally when I do my k, that's an addition. Okay, so this is just standard matrix manipulations. And I'm going to go with a slightly different color. So now if I start with k here, k, I'm going to go down to y. Okay, and then, oops, wait a second. Nope, 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 nope. I was about to do it wrong. Let's say undo, 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 undo. Okay, so now I'm going to go k all the way out to the x. Okay, and now I go x py y px. Okay, great. Okay, so now that's going to be x py minus y px times vector length k. All right? And so now what does all of this stuff get at? Well, what we have now is a total orbital angular momentum operator. And what becomes useful is now for us to think of each one of these as the two-dimensional representation that we talked about earlier. So let's go all the way back to, yes, to right here, okay, when we were doing this two-dimensional. So now you can see this is where these two-dimensional results come from, okay? And you also, hopefully you recall that the eigenvalue for each one of those was MLH bar. So what we can do with this now, let's see here. So I'm going to call this I component, so this y pz minus z py, I'm going to call that Lx operator, okay, times the I vector, right? Minus, and then xpz minus z py is going to be Ly operator times the j vector, okay? And then now we go plus for the k dimension, which is z, and xpy minus ypx is going to be Lz times the k vector. And so now if I had a picture that looks like this, right, where you can see I have this particle that not only has projected magnitude in the z-y plane, it also has projected magnitude in the zx plane, and it also has projected magnitude in the xy plane. Okay, so this would be my total operator that I want to use. But something interesting is going to happen, okay? Oh my gosh, look at that. I left myself a whole blank space. So what's going to happen now is, so recall that position and momentum are suspect to Heisenberg uncertainty, right? So each one of these terms, ypz for example, that's going to have a Heisenberg uncertainty. Zpy, that's also going to have a Heisenberg uncertainty, right? Any of these terms in our orbital angular momentum operator are going to be suspect to Heisenberg.